wow, it has disappeared. Damn it, where is it? Wow, it has disappeared. Just a second. The meeting has disappeared. Where is the window? Just a second. The meeting has disappeared. Where is the window? Just a second. The meeting has disappeared. Okay. So if I, okay.
The only thing
okay. Okay. But here I'm asking if I do share screen now. Share screen.
And now you select.
But then but it's on another screen here. Is it going to the right one? And now I do that. What do you see on Zoom?
No, but you have to press the so there is a button. You have to share there.
But is that the right one? Is that the right screen? It's going to share this.
No, I think you have to select.
Why? Why do I see only the first one? This one, maybe.
No, because that one is going to share the screen.
Yeah, I want to share the screen.
Yeah, but I mean, it's going to share try that one.
Because I have another one I would like to show afterwards. Oh,
okay.
I see desktop one. But
try desktop one.
Yeah, share.
Go for share. And then
what do you see on Zoom?
I'm going to check the screen. Sí. Por la villa.
Do you see?
No, I see a black screen.
You see a black screen?
Yeah, I only see black here. I see a black screen.
And there is a lot of echo. Hello. But it's telling me I'm sharing it, the right screen. You are sharing this one?
You are screen sharing. Yes, but why? So I see everything black in the Zoom.
I can
try stop share and let's share.
And now we can go where the one. I don't even know where the Zoom
is. It's here. Yeah. Okay.
But I don't see it. Where is it?
Bueno.
¿Dónde está el Zoom?
Aquí.
Aquí.
Al botón verde. Y ahora selecciona la presentación.
La presentación, yo hago la presentación. Ok, share.
Ok. Y ahora entra en modo presentación.
Que está aquí.
Ok.
Hello. By side, yes.
So you're going to be here for 1 week?
Sorry? Yes, yeah.
No, I don't see it full screen. I see the window.
I don't know why. It's too complex system.
Let's try. Normally, when there are two desktop, he shows in the options to desktop. Try to
Swap display? Oh, no.
no. Stop sharing, and then let's try to share again. But
I should have launched this Zoom here on this screen. Ah, but here I have it. Okay,
yeah, this is not the main menu. This is the small one.
You are sharing. Stop sharing.
Exactly. Now there.
Here, this one.
Yeah. And now put this window here in the middle so I can see a bit better. No, the small white one.
Yes.
Because normally when you have two desktops, he may show there desktop 1 and desktop 2. So try to go below.
But I don't understand. If I select my PowerPoint, why it doesn't select it?
It's selected, but it shows me not full screen mode, but all the window with all the we can do it like that if we don't manage.
Do it like that. Now I'm sharing.
Yeah.
Because here it's fine at least.
Yeah. Yeah. Okay. So we can do it like this. It will be recorded anyway, and we will have the presentation. So sometimes you.
but you see something.
Yeah. I see the screen,
Yeah.
but not in full screen mode. Just that difference.
This one.
Yeah. I see this with the whole menu and the whole window decoration. So no problem. We do it like this. Sometimes these programs are complicated.
Yes. Yes. Wow.
I'm going to look for a laser pointer.
Okay. Thank you.
Así, bueno, claro, como este es suyo. No, perdona. Como ejemplo de
This USB. No, we have.
And how do you remove this here?
You have to you have to find the mouse. Okay, let's try. It's there.
Yeah. Oh, yeah, good.
Got it.
Maybe yes.
Okay, it's not changing.
Oh no, I use this to see.
Okay, then this one.
Well, does it work? Yes, it works. Yes.
If you press the upper one, you have the
No, upper one.
It's a new adventure.
Yeah.
Okay, so let's turn off the lights. So let's start. Welcome to the seminar today. We have Bruno Altieri from the ESA Science Directorate. He will be visiting us during this week, right?
Yes.
So he's in the visitor's office. And today he's going to talk us about the extragalactic service with Euclid. And please.
So thank you very much, Juan. Thank you for your invitation. And it's a pleasure for me to be at SEFCA. So it's the first time. And we have lots of things in common to share because you are planning big surveys with Alambre Observatory and about to start an exciting mission, hope launch in July. In July, this year, 10 years of preparation. So just to recap, that cosmological mission, the system has been set up for our cosmological level, which is described with very few parameters. So you use a fantastic level of the lambda CDM with the dark energy and dark matter, and there are still some known, but it's what explains best our universe. This is the first light from the universe, you know, from the CMB, and we want to know how these CMBs, how these inhomogeneities, these slight units have evolved. The big unknown is to model, as you know, dark energy and dark matter. And we have still no idea what those are. It's 9% of the energy content of the universe. And these two entities have actually different. The dark energy is making the expansion, and whilst dark matter has the same property as the baryonic matter, that it tends to attract and make structures possible in the evolution of the universe. So and the dark matter, the dark energy really had some effect from redshift 2 to 1, which is the redshift where the Euclid will be mostly observing. So, no, I will skip this one. So, two main probes are for this telescope is dark matter and dark energy is the weak lensing. So, as you know, that we are mostly known. Acknowledged to strong lensing, where you have the strong arcs, which is a light of a galaxy, background galaxy, deflected by very strong masses. But in the weak regime, you have very slight distortion, and this is what you can use to, and statistically on thousands of galaxies, to map the masses. So if you had such a grid, this is what I usually show more to students, a grid of galaxies, and you put mass in between this background grid of galaxy and us, you will see that they are deformed by the weak lensing. And from there, you can reconstruct the potential of the mass and see where the mass is. And you can do a tomographic view of the universe by selecting galaxies at different distances. So where are these masses and how they evolve? So this is only the main problem of Euclid. And the other one is the baryonic acoustic acceleration, which you can also observe with ground-based telescopes, of course. But we want to do it at higher redshifts. So these are the input of these fluctuations that have been evolving since the time, and you find this baryonic acoustic 10, 20 years ago with Sloan and several surveys by now, and we want to do that in space. So these are the two main probes. The third probe is the galaxy clusters. But for that purpose, the idea is to build a telescope which is modest. It's only 1 to 2 meters. Now James Webb is 6.5, and we are in the area of the 8-meter telescopes. But it's extremely good PSF, optical quality. It's a Korsch telescope with an astigmat 3 mirror, so that there is a very large field of view and very small distortion. And it's very homogeneous PSF across the whole field of view. So we get a PSF below 2 arc seconds, 0.14, 0.18 arc seconds, and very stable. So to have such a stable configuration, it's all the whole structure is in silicon carbide, so it's static. It doesn't deform even with small temperature variations. So this has been constructed by Astrium, and then you need, of course, the optical part, the payload, and the instrument. And the instruments, so the main one, the first one is this instrument, which is CCDs, a camera with CCDs in the optical, a very large band, and it has extremely good PSFs. And then the other instrument is a near-infrared instrument that do both imaging and spectroscopy in 3 bands. For the first time, we will have a full survey of the extragalactic sky in Y, J, and H band, and also slitless spectroscopy to get the redshift of galaxy, mostly in H alpha. So we are targeting the redshift beyond what can be done on ground. You can usually use H alpha up to redshift below 1, but here from 1 to 2 micron, we are mostly targeting H alpha, but other emission lines, like to get the redshift of the galaxy, to get millions of galaxies, several tens of millions of galaxies with a spectroscopic redshift. Now, this slide is a bit outdated because actually the solar panel is straight now. It doesn't do this angle now, but you can see where the 2 instruments are, and you have the high gain antenna, the low gain, and the shield also affects to get a very isolated telescope from a thermal point of view. So I have a few pictures from the construction. So this is a mirror after it was polished, and we have this dichroic mirror to split. Very important to split at the same from the to the optical band and to the infrared. This is very important. So this camera is 600 megapixels, 0.1 arc second. So it's barely sampled, night pre-sampled, and and it has a very large field of view of 40 by 40 minutes. So just on the JPass field of view is also very wide. I guess the pixels are a bit larger. You don't need a 0.1 pixel, 0.1 arc pixel there. And this is the CCDs. The CCDs are 4K by 4K. Now I think you have bigger CCDs by now. We also use the same E2V detectors coming from Euclid. And so we have 36 of the CCDs. Of course, yes, compared to Rubin, LST, it's small, but this has to be in space. So 600 megapixels, and now it has all been integrated. And the near-infrared instrument is working with other type. These are not CCDs; these are CMOS detectors, and this is integration. So you need the filters, you need grids, so you have the grades of done in Marseille, in France. And so we have different filters and the gratings. Now, unfortunately, one of the two gratings has been mounted. They have observed spectroscopy, so everything is dispersed. So you get the spectrum of all of it, but you do it you want to do it in 3 directions, but one of the grating mounted in the wrong direction, so it doesn't work. So we will use the other 2 and play also a bit with the angle, by a few degrees, to make decontamination of the spectrum. So this is what you get. This is simulations, of course, but you get all the light from this image. This is an image in the near infrared, and you disperse all the light of the detail. So, of course, many spectra can overlap. So you need to put 4 different angles to decontaminate. So I have a few more pictures of the integration. That was last year of the telescopes. It was for a long time in Torino, and now where it was finally integrated, the payload module and the service module, and moved to Thales Alenia for final test. It's in a big chamber, and we're doing the thermal test and radiation test also. And there have been just want to show you some nice pictures where they are re-inspecting. You see the secondary mirror of the secondary from the first mirror of the latest images. And that's the final integration. I think by now we are just completely finally integrated now in Cannes. And we'll go to the launch site, which was supposed to be in French Guiana, but on the Soyuz rocket. But as this rocket, obviously, with the war is not available anymore, we had to change, and I'm launching with SpaceX, Falcon 9, and so it will move by boat probably in April this year for launch as early as July. The adapter are still, we had to change a lot of things, but the adapter for the rocket and so on. But it's now we are doing in the in February there will be an event where for the media. The last time it will be presented to the media. And this is the orbit it goes where I'm trying to put here on this. I took slide and you see the Earth into scales, and it's going to L2, where most of the mission, the James Webb, and where there also it's a nice because you have the Earth and the Sun at the same direction. But a point where it stays there, it's making a big halo orbit, and with a minimum of energy, you can stay in this orbit. Actually, it's inclined here. You don't see it. It's not perpendicular to the ecliptic. It's a huge orbit there. But as soon as it goes there, we can start. Even on its way, we can start the commissioning. So it's 4 times the distance to the moon, so 1.5 million kilometers. Now, Euclid. And it has an unprecedented PSF in space. I mean, it's almost like a Hubble, and although it's half the size, but and a large field of view. So there's a huge potential for legacy science. So if you compare the field of some famous field, you can see that we are of course much bigger. But yes, the JPAS field of view is even larger. Now, what part of the sky are we going to observe? The extragalactic sky, of course. It's a cosmology mission, so we avoid the outer galactic plane and the ecliptic plane. where mostly because of the in the near red, there is too much light, so the background is too high, so the sensitivity will be less. So this slide from Jean outed, but you that starting from the poles, actually mostly from the south from the south pole, going toward lower with the years toward the lower latitude. So two main gaps and two islands between the and white field I touch we always the same sequence. So we stay about 1 hour and go to the next one. So we do 2 and for 6 years. So it's over 15,000 square degrees and of wide survey, and about 53 by now it has changed, 50, a bit more than 50 fields were 3 deep fields. The ecliptic deep field north, south, and the fornax, which also covered by Ruby. And on this field, we go to magnitudes. So instead of going to magnitude 25, typically, 20 depends up to the galaxy, but it goes to magnitudes. It's very useful also for internal calibration, that we have a good purity and completeness on spectrum, this field. The first field that will be made public in the quick release 1 will be on the deep fields. So, yes, just to review, this is, of course, we avoid the galactic plane. That after the 6 years, there might be some surveys where we do micro lensing or time transients, maybe but the first 6 years is where we have the absolute accuracy of the telescope with, for the positioning. It's called gas, 6 years of consumables. So you have to keep, it's not have to have a very good PSF, but the positioning of the telescope must be extremely accurate within 20 milliarc seconds or better at most. So we use cold gas for that, a lot of little thruster. And once it is finished, the cosmological survey, maybe it can be used for other science. Now, what's very important is that we have exquisite PSF on an unprecedented large size of field, but and 3 near-infrared filters. But for photometric redshift, it's important to get the same area covered by ground-based survey, and they have started already years ago, and JPAS was one of them, although probably it will be on a much more reduced area because the area at the north will be more covered by Subaru. But in the south, eventually it will be, in the north we have Pan-STAR and CFHT, in the R-band and the U-band. The south it will be mostly Rubin, LSST. But I will use data from Tolo photo from the dark energy survey, of course. So this plan of the data years ago in progressive, it's not all these ground-based surveys. And I like this slide where it shows what Euclid will be able to do, that a galaxy at redshift 0.1, this is how we would see it with Euclid. Of course, we have space resolution. But Sloan, which is the run so far, after so many years, will redshift 0.1, which is already half the age in, you know. So, we do a lot. Shows this can this is on square degrees at this resolution have been observed in 30 years, and we're going to go with 15,000, one third of, and James Webb, of course, goes much deeper and do fantastic things, go to the near infrared and mid infrared, but only Euclid at this resolution will observe so much. 1,000 times the area of HXT. So for instance, this is also, it's like we have more strong lenses, but although it's not one of the fundamental cosmology probe of Euclid, but you can do a lot of cosmology with strong things, and we know a few hundred now, but this is what we will do after 2 months. Euclid, we will discover every square degree many lenses, and there is some programs to follow them up with FORMOS and other telescopes. Because what have also mission with have very high quality, very stable data, and we can find very rare objects and in numbers. So this is the power of Euclid for the future. But as I said, we will need ground-based follow-up first to support the photometric redshift, which is fundamental, but also later on for all the objects interesting that we know. So for Earth, wave, ELT, of course, moons, all this fantastic influence on this Metas telescope. So at ESAC, we're a team, and we are building up experiment a bit on Gaia. This is a one-to-one model of Gaia around us. So people have left the team are joining, but this is we do the mission planning, the look analysis, we build the road, and it is sent to the consortium is Euclid, 500 by now, but not all are active, 100%, but mostly engineers, scientists, in this in charge of the data processing in 10 science data centers, 1 in the US and 9 in Europe. And even we are all the data so the team at ESAC is rather small. And we have a lot of science working group on different cosmos, and we meet once this year, consortium meeting. And I will not talk about, well, maybe in the second presentation I have a bit more on the data processing, but it has been divided in 10 units to reduce the optical data, the near infrared data, the spec, to merge all these images and quad all of them with the ground-based images, do the shear analysis, the photo Z analysis, spectroscopy, and then finally to go to the LE3, which is the cosmology product, the power spectrum. So we are almost ready. This is just a summary of the capabilities of Euclid. A modest telescope, but very ambitious because it will open an area to also infrared to this on base. So we are very enthusiastic from that. And this is the first part of the talk. Then I'd like to talk a bit more on the archive, which we're developing. So that works. I have to switch to the other application. My log to the yes, that also works. So what we focus at ESAC is Sarah Nieto, the main engineer, and we have also many other colleagues from the ESDC, the Science Data Center at ESAC, is to build the PetaByte. So actually, we have two archives. It was died early on. The consortium has its own archive for the data processing. So it's a metadata archive where everything is registered and the files are stored in a distributed storage system. And it was developed by the Groningen University. It's an evolution of AstroWise, which is the system they use for many other ground-based survey, like KISS and ST. And but we based on the experience of Gaia and we had a much more simple archive where it's more intuitive and where only the final projects are registered. In DPS archive, you have everything. So the whole integrated product, it will be reprocessed many times, and it's very, very complex. You have to access it. And now at ESAC, we're a data labs infrastructure, both a collaborative platform where you can access being close to the data because the data that you download is. So we are using Jupyter notebooks to work with it very close. So yes, it's just like to see that we have all these data centers in Europe. So with them, level 1 is what for data. It is sent to the consortium, and we retrieve them, level 3, just in the ESAS, ESAS archive system. And it allows to visualize with Aladdin Light so far. In the future, I hope you can use directly the feed, so you can play with the dynamics. You can download the product, you can visualize, you can query the catalogs, you can download the spectra. I've also developed an image cutout space. People want to manipulate so big images. So this is a very important thing to do. And these are the different products. I don't want to see. So this is the way this is a link page where you can go either to the science archive or to the data processing archive. And I will not talk about the data processing archive, but I will keep to yes, a bit on technologies that we use. So we used to use in many missions Postgres data, but going into such amount of data, we have to move to a solution of Postgres, which is Greenplum, which is open source. It allows processing, parallel processing of data. So the database is distributed in different nodes. And we have the Dell Elite petascale data storage using NetApp before, well, gradually moving to this data center. Then we have all these intermediate API, which are all VI compliant. And from there, the web portal where we can access the data. So that the web portal use all these compliant VI to access the data. And we have the data labs. So this lab tested, Gaia will also move that. Gaia hasn't done yet in the operational life, but it allows to with ADQL, which is the astronomy data query language, query catalogs which have big sources. This is the main interface. Well, of course, all the consortiums will see the data at the beginning before first public data. Can query with some simple queries. You can get your observation and to download. Also with the catalogs. So far, we have different catalogs, many catalogs, which we want to make a flat one where you will have information that hasn't been done yet. Because what the consortium delivers for MER, for photosets, for spectra, for ecology, they are all in different catalogs. So you will need a lot of join to manipulate them. So this is what we have so far, but we will build a flat catalog in the future. So it's really, this command line DQL, which can be used in AstroQuery, is really what most of using for Gaia. 95% are done with AD. A lot of experience, a lot of cookbooks. We will put examples on the help page. So, and it's SQL adapted for this is additional interface. So it takes learning at the beginning, but it is. So we have only simulator so far in the archive, and you download the observations or the is the concept where all the sky has been of certain time, and on one tile, when you have many observations and ground base, over the they are really sampled all and using the geometry, and it's your quad. So you get both the individual images, the stack images, the instrument, and then everything which has been optimized coad of mosaic. And you can catalog and your source, the sources on time. So since you showed me that you can do that also on the JPAG. What I'm not sure if you can download it. So this is what we want to, you can play, interact, and then down the catalog after you make your choice. In this latest scientific science, we patches, and you can set bound, and then you can zoom in the sky, see this day of the observation of the time, see the original observation, but then pre-tied in terms of, and you get the mosaic, and then you can really visualize. So I encourage you to log in. And there will be some command line. So far, we haven't put much effort on AstroQuery, but so you can do this just with the command line. It's all in the help pages. To get your observation, to get image data, to get or catalog queries. And okay, I will not speak too much about that, but we are working for many cases for the Euclid archive to work with data labs. Some pipeline system object will run on this data. It will allow for some teams to interact, have their Jupyter notebooks close to the archive, and access the data more easily. We have some alternative packs also. Or if you want to run machine algorithms, there will be CPU cluster. We need to get a fund for all this. This is the idea. Because data, one this image is 13 gigabytes, one single image, a quad image. It just doesn't work. You cannot download the data. So if you want to do that, it will have to be close to the data. This is a advantage. So this is the feedback in the pages from the there was a list to the year before, so how you can even this only thing so far of this test, not test, but people to use them to get some feedback if I'm missing something or some functionality. So get some feedback. And it's challenging. Only a few months things that do not work perfectly, especially the data processing system, which is the core of the mission. If it doesn't work, we have a problem to process the data. It's yeah, we're ready and very enthusiastic about this mission.
Very strong questions.
So apart from the deep field, maybe the north of the
yes.
The rest of the sky, saying that.
The idea to be heterogeneous for exactly the same depth. Typically magnitude 24.5 for one galaxy, we are still in the shape of the galaxy, and deep fields. Then there are calibration fields. Cal field, a bit in 90% of the time on this white field and field.
And I have a question. I assume because this is a cosmology,
yes.
Things your galaxies from the Milky Way cannot can be arbitrary for something like segmentation maps and whatever, or are you planning also to add some kind of ESA autonomy or something like my question would be to do local group science somehow.
So there is a working group on the local universe. It's true that the main processing is tuned for galaxies. So not for stars or low surface brightness galaxies, which will be filtered out. So this is why we have this idea of an alternative pipeline that will keep most of the information which is lost that the cosmology doesn't need. For stars, we do different types of photometry, aperture photometry, PSF matched photometry. Of course, you cannot do bright stars. Bright stars, they saturate already at magnitude 12 or 13. And they create ghosts, of course. One of the main things that we have on any ground, you must have that on JPass as well. But stars, yes, is more for the cosmologists is more nuisance, of course, than anything.
Of course.
And
I love these products, so I'm used to that.
But also, like the solar system object, there would be hundreds of thousands. Anything which is moving, so we want to find them. But yes, the main problem we have, and we are trying to tackle with Muhammad, that data processing is tuned for cosmology, and they don't want to change it. They don't want to adapt it. And so we probably will have to, beyond the mainstream one, we have to develop an alternative one that where you can do science in legacy science.
Yeah, the default pipeline for result systems is terrible. Yeah, we have the Milky Way, we call it the Milky Way science group. So they're mostly for the resolved systems, and they have a lot of problems with the default pipeline, because when something is like a resolved, let's say galaxy, where you actually see the stars, and you want to do the measurement, because they're all detected in one object, in the catalog they're going to be like only the 2 or 3 brightest, not the whole population of resolved stars that are in this large detection. Something like globular clusters on the ground. Yeah, but so yeah, we're also planning to do that.
Again, a little bit on the data management and processing. Actually, I have 2 questions. The first one is more, so you get all the raw images from space.
Yes.
And then you distribute it to these different data processing centers. You distribute it, basically you distribute it through the internet, but isn't it like the same problem that you would have by serving the images in the archive? You are commenting that serving an image is gigabytes.
Yeah, but the level 1 is still not big. We are taking about a few hundred of gigabytes per day. Usually, direction, but for Euclid, it's a data explosion. Then, when you go to level 2, level 3, it goes from gigabytes to petabytes. So first, we send the level 1. Well, there is a raw level 0, but level 1, we have put housekeeping and it's in a FITS format extension. This is sent to the consortium. We make 2 copies immediately. We keep one at ESAC, but this we have seen that okay, we can manage with the bounds. The problem for me is more that to retrieve first the level 2, because it will be about 6 petabytes per day, and then it's fine. I can keep size it so that you have Aladdin light. The catalogs is not a problem. But then how to distribute the data? Because if we have tens or hundreds of users, I mean, the bandwidth of ESAC will just collapse. So, and other projects, so we don't know. So we have to use that CDN, like Gaia. So the data are in other nodes distributed in Europe. But we have to be careful when the data are proprietary for the first 2 years. It's not completely clear how we're going to handle that. But yes, the problem is really bandwidth. I'm fighting with the bandwidth. At ESAC, we have a 10 gigabits line to the Red Iris from Spain, and that we have to share with all the products. And now Euclid is coming, and then well, you have to pay, or it's not clear how we are going to do that.
The other question
all data will be in IPAC, at least in the United States. IPAC, we have all the pixel data and the catalogs. This will also be. And in CDS, in Strasbourg, there will be the catalogs, but not the images, not the pixel data.
The other question I had is somewhat related to what you were commenting on, having two pipelines. So that basically, does it mean that you're going to double the science database, or going to have 2 science archives depending on which pipeline has been used, or perhaps you're going to make a merging of these 2 pipelines, or the results of
You have to think about that. I think, I mean, if the output is our MER mosaics, we have to duplicate that. It's a different product. It's the same structure, same metadata, so we can with minimal, but it will be the mosaics for cosmology and the mosaics for legacy. We have to duplicate. Yes, disk-wise, storage-wise, that's a lot of data. But yes, we have to get the funding for that. Yes, we need.
Good luck. Good that ESA has more money than Safeguard.
So you mentioned several times that you have to be ready for launch. Which are the things that must be solved before the launch, and which are the things that can be adapted that required after?
So the first thing is that the DPS, this data processing system, which has been developed in Groningen, and now all the server, they were also a bit lacking funding for operations. So all the servers, it has all moved to ESAC. So we have the two archives at ESAC. And it's a very complex system. So it has to work and be able to process data. So every time you run it in Europe, in any center, but then everything which is producing and stored there is registered in this archive. So it's complex. I don't want to enter in the detail, but this is the most fundamental system that has to be operational. The science archive comes after that. I mean, at least the data will be first stored in the DPS. And then we need to have the bandwidth. Yes, the bandwidth. Of course, also what is fundamental is to be able to build a survey. It's very complex to build a survey, to have all the sequences. So we're doing a lot of tests now, and even the science operation verification test with the spacecraft itself. Of course, we don't get data now, we get only dark or biased, but we can prepare that all the timing of the sequence are ready. For the wide and deep survey, we are more or less ready, we think, because we have worked on that for many years. But the first few months, the commissioning and the performance verification, it's extremely complex. It's non-standard. Just like when you commission a new instrument, you do a lot of things which are new, especially for the calibration of the PSF or the phase diversity. It's very complex. And yeah, we are testing all these sequences now. It's a lot of work, yeah.
You mentioned that you will start the observation from the South Pole.
From the south, the first observation will be calibration, calibration fields for photometric calibration and spectral calibration. But the wide survey will mostly start from the ecliptic poles, because these are the two areas where we have most visibility and where we have already data, ground-based data. And gradually, with the year, we go from the two islands, from the two poles towards lower ecliptic latitude, yes. So in the south, the dark energy survey has covered already 4,000 or 5,000 square degrees of this area. And,
will we get Euclid data in the JPAS footprint in the first year?
sorry?
Will there be Euclid data within the JPAS footprint in the first year, not from commission?
I have to look at.
It's in the north.
It's in the north. Yes, yes.
Likely depends on the JPAS footprint.
Yeah. We'll start more in the south than in the north because we have more data actually, because yes, the big telescopes are in the south. Also, we have Pan Star in the north, but it's 2/3, 1/3 roughly, according to the latest plans I've seen. But
some should match because
oh yeah, there will be a lot of match. Yeah. Yeah, the first public data release is after 2 years, and it's 2,500 square degrees. There will be a few data releases before, just to give an idea of the observation, nice galaxies, and the first pass on the deep field, but only one pass. There will be 40 passes to go deeper, and that will be after 1 year. But the first big release for cosmology is 2 years after launch, so it will be N20. And 25. But within the consortium, yeah, we will have this data 1 year before, not with the final processing versions. That's not clear. In the SAS, it's not even clear how many processing versions we will store, because like for Gaia, you can still have the data release 1, 2, 3, but we will, and then for Euclid we'll have the same, and we'll keep them for legacy. But all intermediate data version in between, we have to scrap it. We just cannot keep all the storage for it.
I was going to ask about the data releases.
So there might be public data if everything goes well already this year. Just some nice galaxies. We call it ERO, early release observations, where we make nice public images, just like James Webb did, and the very large galaxies. Jean-Charles Cuyand will be very much involved into that. But then after 1 year, there will be the quick, we call it QR1, quick data release 1, which is on one of the deep fields. I can't remember which one. And it will be 50 square degrees. So people can plan already, download them, test their scripts, and then DR1, 2 years after launch. Okay, 2 years after the PV, end of the PV phase. So that's actually 27 months. The first, yeah, big release. And there will be 3. Then the second one is 7,500 square degrees, and the DR3, which will be 15,000 square degrees. Wow. Plans may change because DR3 will be 2030, I think.
I have a question. Do you plan to have some kind of archival research proposal for, especially for those science cases that need different processing, but maybe they don't need the whole sky, or so people that need us to reprocess the data for a particular science case? Do you plan to have something like that?
So generally at ESA we have an archive research program already, where every 6 months you can apply to come. And but on Euclid, it's the pipeline are so complex to reprocess by tuning, changing something is so complex. It's one of the things we plan to do for this extent, low surface brightness, but it's very difficult. So to do some other things like that, it's very difficult. Now, the idea is, in principle, is only to have the products given by the consortium. Although some people may say,
that's what I mean. You would apply, and then you would go to the center where they help you to.
Yeah, but we don't do the pipeline at ESA. That's the point. It's a consortium. It's distributed.
So like if this is in France, Mary is in Italy, and Mary is in Germany. Yeah, the expertise to run each one of these steps is a different country.
But maybe eventually there will be some facilities at ESAC. So at least, well, the pipeline can be rerun by changing something on a smaller area, for instance. Yeah, we'll see. Time will tell us.
Okay. More questions? No, we thank again, Bruno. Thank you very much. Very nice talking. Was there a question?
Tanto tiempo.
There was a problem.
Hoy tenía la mañana, bueno, aún tengo ahora una reunión, voy enlazando con otra y justo llegar a tarde también a las tuyas, tenía que terminar una sesión. Pero bien, ¿qué tal?
Bien, pues mira, la atención va a ser un año intenso,
Ya.
súper atención.
Sí, ya me imagino que Bueno,
muestra cosas buenas, pero vemos que hay un montón de cosas que no funcionan.
Ya.
Estamos entrando
Modo pánico.
Pero creo que cada vez más.
Sí, sí, yo creo que sí.
No, el problema es que está.
There is a network here, and another one coming here. And he doesn't allow me to log in. We tried
conocimiento de
La colaboración entonces viene y mejora los productos finales, claro, complica, o sea, el resultado final puede que sea, porque si no, ya, es mucho.
Ya, yo hoy no puedo porque
I don't know what I didn't change anything.
Mañana,
Oh,
mañana creo que no, pero
And I
jueves
leave my account
le puedo
open.
decir a María
Sí.
le digo que venga con la Rúa y si te que no, claro que sí. Yo ya pensé, yo tengo que además la Rúa la vista era como de este tamaño, o sea que imagínate. Sí, sí, es hasta el viernes.
Hasta el viernes,
Vale, sí, pues yo creo que el jueves por la tarde, yo creo que podemos.
For example, now he's on the
Quedamos mañana para comer.
venga,
Vale,
But
perfecto.
a la
if
1:30,
the
2.
Zoom connection
Vale,
is
vale, perfecto.
managed
Yo
by
voy a la
Google,
siguiente.
ahora, sí.
Okay,
that
okay.
wouldn't be a problem. He doesn't need connection if the system is managing the thing. But so basically, you take this code, you go to the computer, you go to this page, it works. But then he tells me there is another option, so I can my account.
Very weird. Look now. What's happening? My computer, the system.
Maybe now it works. You set my password. It was possible to connect with and then when we go to so it says check that this device and the Zoom rules are in the same network. Give me two different IPs, 155, 160. So I don't know if the